What's up guys, here Mr. G with another video for the grade 12. This time we're going to be working with chemical equilibrium. But before we start with the question, please subscribe to the channel so you can get all the notifications and videos I post on regular basis. This is question 6 from June 2016 question paper done at the Northern Cape and Free State. So this question said, pure hydrogen fluoride is sealed in a 2 decimeter cubic container at 693 Kelvin. The reversible reaction reaches equilibrium according to the following balance equation. Define the following terms: chemical equilibrium. Alright, so what is chemical equilibrium? It's the stage where the rate of the forward reaction equals the rate of the reverse reaction. It's a quite simple definition, this one guys, and for sure is going to be in the question paper. Okay, now a reversible reaction, which remember this reaction here, this reaction there that they give you, it is a reversible reaction. Okay, so now what is a reversible reaction? Is when the products can be converted back into reactant. It's very simple as well. Okay, and there is a reversible reaction is when the products can be converted back to reactant, and that is question 6.1.2. Question 6.2, how does the rate of the forward reaction compare to that of the reverse reaction before equilibrium is established? Choose greater than, smaller than, or equal to. It's very simple as well. So what you need to know is that when the reaction begins, you don't have any product at the beginning. So the forward reaction rate is very high. So in this case, it's going to be greater than the forward reaction it's going to be greater than at the beginning, because it's at very high stage. There is not product at the beginning, so everything is going to be forming product. That is what is going to happen at the beginning, right? So the rate of the forward reaction is greater than the rate of the reverse reaction. Let's continue. So far so good. Redraw the following set of axes in your answer book, and on the same set of axes draw a potential energy diagram for this reaction. Indicate the following on the energy diagram: the activation energy for the forward reaction, the value and sign of the heat of the energy for the reversible reaction, and the activated complex. Okay guys, so here you can see that delta H is positive, and therefore this reaction, the forward reaction, is endothermic. You can see that the forward reaction is going to be endothermic, and therefore the reverse reaction is going to be exothermic. So those are important details here to know when drawing the graph. Therefore, the forward reaction, we draw the following there, which is the forward reaction, what they want. The forward reaction is going to be the energy of the reactant at some point is going to be all the way up to activated complex, and then it's going down there up until that point. This is the graph for the forward reaction they want there. Now, the activation energy of the forward reaction is going to be from the energy of the reactant to the activated complex. There is, let's just fix this one here. This one here is the activated complex, and the energy that is going from the reactant, energy of a reactant, to that point, this one here is what we call activated energy, which is E. I'm going to call it the value and sign of the heat of the reaction for the reversible reaction. Now the change in enthalpy is going to be this one here, from reactants to product, but this is going to be the same one as the other one in the opposite direction, and therefore this one here guys, this distance here is going to be the change in enthalpy, right? That is the change in enthalpy of the heat of the reaction, but that one is going to be equal to minus 542 kilojoules. Okay, that number is given to you, but it's negative. Remember, I told you the forward is if the forward is here we are. If the forward is endothermic, then the backward is exothermic. So for the exothermic, then the change in heat or in enthalpy, the heat is going to be equal to minus 542 kilojoules per mole. Is the opposite. Okay, that is all you need to know. And guys, that is what is here at this point there. Okay, so that is the question. I think this is the activated complex. We already marked the activated complex is here at the back on top. That is the activated complex of the reaction, and this is the graph. Okay, so that is question 6.3. Let's continue at question 6.4. At equilibrium, it is found that 0,0 mole of fluorine is present in the container. Calculate the initial amount of mole of HF sealed in the container. The equilibrium constant is Kc. For the reaction is this number. They give you the equilibrium constant. So to answer this question, we are going to complete the Rice table. Okay guys, so for this question we're going to complete this table, which I call Rice table. And using that siglas at the beginning here, you can see it will help you to remember that it's called Rice table. So reaction, initial the mole, in the change, equilibrium, and equilibrium in concentration. Okay, so this is how we're going to complete. And let's start by seeing what we have. The question said that equilibrium, it is found that 0,05 mole of fluorine is present at equilibrium. So at equilibrium, you know that the amount of fluorine form is going to be 0,05 mole. Now this one, guys, is given to you. What else is given to you? Calculate the initial amount of mole of hydrogen fluoride. This one is what you are looking for. I'm going to give this one the value of X. I don't know that one. And the other data they're giving you is the Kc, which we are going to write here outside, right at the bottom. The Kc is equal to 3,5. That is the Kc. Okay, so this is what we have, and therefore we have to start completing this table using this one. So let's begin. Okay guys, so when you start this one here, you remember at the beginning you actually don't have any of these products. So this one is going to be 0. So there is not going to be any product at the beginning. All right, so that is important to know. Now, you have at equilibrium a amount of 0,05. It means that the change from beginning 0 to that one was a positive 0,05. Positive means because it was formed that amount. Okay, now important at this point here of the change is when you can use the ratio. So here you are going to use the ratios, and the ratios are 2. I did not write here the ratios. Let's write it 2, 1, and 1. That is the equation. So the ratios are 2, 1, and 1, which means that the change for hydrogen gas was exactly the same. It was a positive 0,05, and this one here is a double amount. So this one is 0,1. That is the amount that was changed there for the HF. Here you are using ratios, but this is a negative change. All right, so you must know that the change is negative because the product increases, but the reactants decreases. So it decreases by 0,01. That is what I want you to know. And then, guys, the rest is to complete this table. Okay, it's not so difficult. Here is going to be 0 plus, I'm going to write it even though you don't have to, plus 0,05. Therefore, it was 0,05 mole. That is what is at equilibrium. Here, the change you don't know because you don't know the initial, but you know that at equilibrium you will have X amount, which is the initial, minus that 0,1 change that you have. That is what you have here at equilibrium. Now we are going to the concentration at equilibrium. How do you calculate the concentration at equilibrium? So how do we calculate the concentration at equilibrium? We're going to use the formula concentration is equal to number of mole divided by volume, and we're going to use the formula in each of the different columns there or cells there. So in this case will be x minus 0,1 divided by 2, which is the volume, guys, and in each of them then you will have to calculate the 0,05 divided by 2, which is equal to 0,025, and guys, here is going to be the same 0,025. All we have to do now is to use the Kc equation. Now remember, the Kc is going to be equal to the concentration of product divided by the concentration of reactant. Here you can only use gases and aqueous solution, guys. So if you write the expression, the correct expression for this reaction, you have that Kc is equal to, Kc is equal to concentration of fluorine or hydrogen, it doesn't matter, multiplied by the concentration of hydrogen, both of them to the power 1, that is the ratios, and then concentration of hydrogen fluoride to the power 2. I'm going to show you the power 2 is because of the number at the front, guys. It's quite simple. So if you substitute the formula, the Kc is 3,5, and this one is equal to 0,025 multiplied by 0,025 divided by x minus 0,1 divided by 2, everything to the power 2. Guys, this one is a very simple calculation. You are going to finish it. I'm not going to finish due to time, and then you will get at the end that x is equal to 0,13 mole. That was the initial amount of hydrogen fluoride that was sealed in the container. Guys, this is the end of this question. Let's carry on. And we're going to go to question 6.5. The temperature of the reaction mixture is now decreased. How will this change affect the following? Now, remember, temperature is one of the factors that affect the equilibrium. But let's go quickly back to the reaction here. Let's go back to the reaction here. The forward reaction is endothermic. So an increase in temperature will favor the forward reaction. If you increase the temperature, the forward reaction is favored. If you decrease the temperature, then the reverse reaction is favored. That is important for us to understand here because of the type of reaction we are here. Okay, so if you decrease the temperature, what is going to happen, guys? What is going to happen here? The reverse reaction is favored, as we said. So the amount of hydrogen and fluorine is going to decrease, and the amount of hydrogen fluoride is going to increase. And that is what you actually have to write there, because they say the amount of each gas. So the amount of hydrogen fluoride increases and the amount of hydrogen and fluorine decreases. That is what we have to say, but we have to explain using Le Chatelier. Okay, so we have to explain using Le Chatelier, and we explain already there on top in the equation. So what will you have to say? Decreasing temperature favors the exothermic reaction. We say it on top there, guys. Here it is. There it is. You can see we say it. A decrease in temperature will favor the exothermic reaction. You can see it right on this side there. And which one is the exothermic reaction? Is the reverse. The reverse reaction is exothermic, and that will end up the explanation for 6.5.1. Let's go to question 6.5.2. Rate of the reverse reaction. And this one is quite tricky. Be careful, don't get confused now. The rate of the reaction is going to decrease. Both rates will actually decrease, guys, when you decrease in temperature. So the rate will actually decrease. Use the collision theory to fully explain this answer. So let's write that explanation and let's do it here below. What is the first thing you'll have to say? A decrease in temperature decreases the average kinetic energy of the particles. That is the first thing you have to say. The second thing you have to say is that less particle will have sufficient kinetic energy now, and therefore there will be less effective collision per unit time, and that is the end of this explanation. Less effective collision per unit time, that is the end of this one there. And then finally, what the effect of decreasing temperature will have on the Kc. And now it's exactly the same. Remember, from all the factors, the temperature is the only one that affects the Kc. That is important to remember. Now, if the decrease in temperature is favoring the reverse reaction, it will mean that you will have less product form, less yield. And therefore, guys, the Kc also decreases there. The Kc also decreases there. Guys, this is the end of this question. I hope you understand. It's a very good question to practice with the Kc. The exams are almost here and it will help. If you think it helped, subscribe for the channel, thumb up if you like the video. I'll see you next time. Mr. G here.